Hey, hello everybody. Hey, this is going to be a video on help with the question of the day for 10, 10, 10, 12, and sorry, 11, 10, 11, 12, and 11, 13. This is regards to free body diagrams and friction. So we're going to start with 11, 10. So with 11, 10, we're going to have a triangle, an inclined plane, and this is going to be 20 degrees, and this is 1.2 meters high, and we're going to have a block. We're going to have a block on there, and that block has a mass of 2 kilograms. Given my lecture on the free body diagrams, the first thing we need to do is to pick a convenient XY coordinate system. And this is going to be similar for all of these 11, 10, 11, 12, and 11, 13 questions of the day. Okay, so if we start here, this block is going to move along the plane. If it moves, it's going to move along the plane. Okay, so we're going to make this direction our X and this direction our Y. Okay, that simplifies things greatly because then we don't have a component that's accelerating both in the X and Y. All right, so the next step is to draw a vector for everything that touches it plus gravity plus friction. Everything that touches it plus gravity plus friction. So now in this case, the only thing that is touching it is the inclined plane. So we're going to have a force, and the force caused by a surface pushing on an object is called the normal force, and it is always going to be normal or 90 degrees to that surface. We don't have an applied force would be, for example, something else that is going to touch it, like we'll see in the next question of the day. So now we go gravity, and gravity is always going to go straight down, okay? And that is equal to mg, which is also known as the weight. Once we also have we want to talk about friction, and we want to talk about any other forces. And in this example, there is no friction. There's nothing else. So this is the only two things. So now we've drawn a vector for everything that touches it plus gravity plus friction. And now we want to resolve our vectors so that they're going in our XY coordinate system. So we can see here that the normal force is going in the Y direction, but gravity is going in both directions, okay? So we're going to, using some trig, we're going to resolve this, and we're going to have that vector and that vector, okay? So if this is 20 degrees, then that's 20 degrees, okay? And that can be easily seen. If this is 20, then that's 70. This is going to be a right angle, so 70 plus 20 is 90. That's 90, so this would be 70. So we could use 70 degrees, but we're going to use 20 degrees. Okay, so now this one right here is going to be mg cosine 20 degrees, okay? And that is the force of gravity in the Y direction. And then we're going to have mg sine 20, and that's going to be the force of gravity in the X direction. Now we have all our vectors, and they are in our XY coordinate system. Now we're going to use Newton's second law, the sum of the forces. So we're going to say the sum of the forces, and we'll start in the Y direction. And that is equal to ma. Now, we can see here that if there was a block on top of an inclined plane, it is not going to sink. It is not going to sink into the inclined plane, and it is not going to levitate off of it. So we know that that is going to equal to 0. We know that that is going to equal to 0. Okay, So we know that the force normal is going up. So we're going to call that positive. And we know mg cosine theta was the component that was going down and opposite of the force normal. And that's going to equal to 0. So now we can say force normal is equal to mg cosine theta. And now we're going to have 2 times 9.8 times the cosine of 20 degrees. And 2 times 9.8 is 19.6 times cosine 20. And we're going to get 18.4. Okay, so we know that our normal force is equal to 18.4. Okay, and checking our question, that is what we're looking for in the first question. Now we want to know, what is the acceleration down the ramp? Well, the acceleration down the ramp, the only force that's going down the ramp, okay, is the one in the x direction, which is going to be mg sine 20 degrees, okay? So now what we can do is say the sum of the forces in the x direction is equal to ma. Now, if this is going to move, it will move down the ramp, right? So there is going to be an acceleration. It's not going to be equal to 0. So this is going to be mg sine theta is equal to ma, okay? And we can see here that our masses cancel out. So we're going to have 9.8 times the sine of 20 degrees, and that is going to equal to our acceleration. And 9.8 sine 20 degrees, and that's 3.35. Let me double check that. 9.8 sine 20, 3.35. Okay, so we know our acceleration is 3.35, and that would be meters per second squared. Now, if you didn't cancel out those m's, right, you're going to have 19.6 sine of 20, then you would divide by 2, and it would still work out to be 3.35. All right, so that is the acceleration down the ramp. And now, if it starts at the top, then at 0, and it's going to drop vertically by 1.2, what is the velocity at the bottom of the ramp? So this is going to take us back to the kinematic equations. And before we kind of get to those kinematic equations, we need to know how far down the ramp it would be. So now we are going to use trig again, but this time we're going to use this distance of 1.2 and this angle of 20. So this distance down the ramp is going to be 1.2 divided by the sine of 20 degrees. If that doesn't make sense, if we think about the sine of theta is equal to the opposite over the hypotenuse, and we're looking for the hypotenuse. So the hypotenuse is going to come here, and the sine is going to come down there. And when we go ahead and plug that in to get a number, 1.2 divided by the sine of 20 is equal to 3.5 meters, okay? So this is equal to 3.5 meters. And now what we are looking for is the correct kinematic equation to solve for the velocity at the bottom. So we're looking for a final velocity, and we don't know that. We know that the initial velocity is equal to 0. We know that the acceleration is equal to 3.35, and we know that the displacement is equal to 3.5. Now, since we don't have time in this, we're going to go to kinematic equation number 4. And we're going to get v final squared is equal to v initial squared plus 2ad. We know the initial velocity is 0, so we can take the square root of 2 times our acceleration, which is 3.35, times our displacement, which is 3.5, and all of that is going to get the square root So our velocity at the bottom of the ramp is equal to the square root of 2 times 3.35 times 3.5, and that's going to give us 4.84. So 4.8 meters per second is going to be our last question. All right, so moving on to the question of the day for 11-12, and that is going to look very similar. We're going to have the same sort of triangle here, except our numbers are going to be a little bit different here, and we're going to have a few more aspects. Okay, so with this being said, I'm just going to erase this and redraw it and put in our new numbers. And we'll see, even though this gets more complex, we're going to follow that same pattern. Okay, so we're going to again have our triangle, and that is going to be theta. So in this case, that's going to be 30 degrees. So that's equal to 30 degrees. And in this case, we're going to have a 3 kilogram block. And now we're going to have friction. We're going to have a coefficient of friction, of static friction, that is 0.578, and a kinetic friction of 0.450. So the first thing we want to do is draw a free body diagram. And so as we went through before, in a free body diagram, we want to produce a convenient XY coordinate system. It's going to be the same XY coordinate system, so the X is going to go along the length of the inclined plane, and the Y is going to be perpendicular to that. So we want everything that touches it, plus gravity, plus friction, plus other. Now, we're not really, maybe one question that we'll ever have an other, and that would be something like a magnetic force or an electrostatic force, something like that. So we're not going to have that. And also, sometimes we're going to end up with something that is having a lot of information, and we might want to draw our free body diagram separately from everything else, not to confuse it. But when it's this simple, we can kind of superimpose our free body diagram right on top of our drawing. Okay, so that's what I'm going to do. Okay, so now, again, like before, that's going to be our normal force. And that is, I believe, the only thing that is touching it. Okay, now we're going to have our gravity, and this is going to be our force of gravity. And now we're going to add in friction. So if this object's going to move, it's going to move down the ramp. Okay, so that means our force of friction is going to be going in the opposite direction. So that force of friction is going to be up the ramp. And now we have our free body diagram, okay? So our second one is to solve for this normal force. And just like before, we want to resolve all the vectors that are not in our convenient XY coordinate system. So just like before, we're going to have this one that's going opposite and this one that's going down. So this one right here is going to be, mg cosine 30 degrees. And this one right here is going to be mg sine 30 degrees. Okay. And now we're going to have 3 times 9.8 cosine of 30 is going to be 0.73. But just to get those numbers, 0.87 times 9.8 times 3 is going to give us 25.46. Okay, so this is 25.46, and that is our force of gravity in the Y. And now on this one, we're going to have 3 times 9.8 times the sine of 30. 3 times 9.8 is going to be 29.4 divided by 2 is going to be equal to 14.7. So our force of gravity in the x direction is going to equal to 14.7. All right, so now we'll get back to the friction here in a second, but to calculate the normal force, we're going to have the same thing. Sum of the forces is equal to ma, but this block is not going to levitate or sink, so we have that same thing. Force normal minus mg cosine theta is equal to 0, so force normal is equal to mg cosine theta, and then just this is where it's going to change from the last problem. So we are going to have mg cosine theta, as we already plugged in over there, is going to be 25.46. We'll call that 25.5 newtons. So that is going to be our normal force. Okay. Now remember, this vector right here going in the x direction is really going right there. So everything is coming off of the dot that we're going to use for our mass. Okay, now we put it down here so that we can emphasize that this is a right triangle and that we can use trig to calculate or resolve those components. All right, so now what we're now going to have, which is going to be a little more complex than the 1110, is we're also going to have the force of friction. Okay. And remember that the force of friction is equal to mu force normal. And so in our mu force normal, okay, we know our normal force is 25.5, and we know that our coefficient is equal to 0.57. Okay, so if we plug that in, we're going to have 0.578, that's our mu, times our normal force is 25.5. And when we calculate that, 0.578 times 25.5, and that's equal to 14.74. 14.74, okay, newtons, and that is our force of friction. So what this question is asking is, calculate the acceleration down the block due to static friction. So now we're going to say the sum of the forces is equal to ma. So we now know, and I'm going to say down the ramp is positive. Down the ramp is positive. So we're going to have mg sine 30 degrees, which we already calculated at 14.7. So this is going to be 14.7. The friction is going in the opposite direction. And then that force of friction, which is mu force normal, is what we calculated there, which is 14.7 and 14.74. And that's going to equal to 3a. And right here, we can say that there is more static friction than there is the acceleration down the ramp. So what we have here, when we calculate this, is going to be a negative value. It's going to be a negative value. And that's going to be negative 0.013. And so if our acceleration is negative, then we're going to have no motion. Okay, so that no motion is going to give us something that is not moving, and we can see that that's barely going on. Okay, now so this next part of the problem. Now, if we give it a little push, okay, now as soon as it starts moving, it's going to go into the kinetic friction, which is usually lower. And we can see here, since we have a coefficient of kinetic friction of 0.45, we're going to kind of plug this in again and see what our acceleration is. So it's going to look very much the same, okay? Except now we're still going to have this 14.7, but now we're going to have this mu force normal, but this time our mu is 0.45 and our normal force is 25.5. And when we calculate that, 0.45 times 25.5 gives us 11.475. We'll call that minus 11, we'll call it 11.5. And that's going to equal to 3A. So we subtract that, we're going to get 3.25, and then we're going to divide by 3, and we're going to have an acceleration. Our acceleration is going to equal to 1.1 meters per second squared. And now that is the acceleration down the ramp. And now it's going to move vertically 1.8 above the ground. What is the velocity at the bottom of the ramp? So now we're going to use this one here, and we're going to do something similar that we did last time, and that is to use our kinematic equations once again. And we're going to have V final squared is equal to V initial squared plus 2AD. And our D is going to equal to 1.8 divided by the sine of 30, which is going to give us 3.6 meters. Okay, we know that the initial velocity is 0, so we're going to take the square root of 2 times 1.1 times 3.6. And now, and we're going to get 7.4. So our V final at the bottom is 7.74 meters per second. All right. So that is our question of the day. A question of the day for 11:12. And then I will pick this video up here in a minute, and we'll do 11:13. All right, hello, we're back again, and now we have some students out there, and we're going to end up going over this question of the day for 11:13. Okay, since they're out there, I've got my mask on. This is going to look in a lot of ways similar to the 11:12. And also even back to the 11:10, which is simpler. Okay, so you obviously have looked at this before you look at these solutions. So here we go. All right, so we're going to have the same sort of triangle. Okay, so we're going to get a couple things that are different. This is going to be 27 degrees. We're going to have a block that is going to end up, this block is going to end up being on this ramp here in a second. Essentially what it's going to have an initial velocity that's 8.5 meters per second, and it's going to be sliding up. So we're going to talk about, hey, how far does it go up the ramp? And so gravity is going to work against us, and the friction is going to work against us. Okay, so this is going to be 4 kilograms, and we have a distance. We don't have a distance, okay? We do know that the coefficient of kinetic energy is equal to 0.4. We know the coefficient of kinetic friction is 0.4. We do not know what the static friction is, which we're going to solve for it when one of the last questions. Okay, so we want to draw a free body diagram. We're going to want to put our convenient XY coordinate system so that the X moves along the direction of the incline and the Y is going to be perpendicular to that, just like the other two. And I'm going to kind of draw my free body diagram right here. Now we want everything that touches it plus gravity plus friction. So the first thing we're going to have is our force normal, which is perpendicular. We're going to have our force of gravity. Now, this time we got to think about which direction our friction is going to be. Now, since this block is going to be going up the ramp, okay, friction is always going to work against the motion or potential motion. So we're going to have our force of friction, which is going to be right there. We know that this force of gravity here is equal to mg. We know that this force of friction is going to be equal to mu force normal, okay? So we need to calculate the force normal. We know our initial velocity is 8.5. We're going to resolve and figure out what those accelerations are before we get and deal with how far up the ramp it goes. All right, so once we have identified all the forces, everything that touches it plus gravity plus friction, which we have done, now we're going to resolve. We're going to resolve any vector that is not in our convenient xy coordinate system. Just like the previous two examples, that's going to be gravity, and that is going to be mg cosine 27 and mg sine 27. So we know that this one right there, that's going to be the one that's opposite. If this is 27, then this is 27 degrees. And then we can go down like this, right angle. So this one right here is going to be mg cosine 27 degrees. This one right here is going to be mg sine 27 degrees. And now essentially what's happened is this goes away. And if we want, we can think of this as being right there. So we actually have two forces. We have two forces that are going against the block. Two forces that are going against the block. Okay, now because the friction is dependent, the friction is dependent on the normal force, we're going to calculate the normal force now. And just like before, the object is not going to sink in or levitate off of the incline. Therefore, the sum of the forces is equal to 0. So we're going to have the normal force. The normal force minus mg cosine 27 is equal to 0. Therefore, force normal is equal to mg cosine 27 degrees. And we know that this is 4 times 9.8 times the cosine of 27 degrees. 4 times 9.8 is going to be 39.2. 39.2 times the cosine of 27. I think it's going to be around 34, 35. 34.9? Okay, so we now know that this force normal is equal to 34.9 newtons. Okay, now we have now drawn our free body diagram. We calculated the normal force. We want to calculate the acceleration down the block due to just kinetic friction. Okay, so essentially what we have here is we're just calculating this. Okay, now I'm going to do this sort of separate here now, and then I will put everything in here so we can calculate what that overall acceleration is. But you'll kind of see what's going on. All right, so my force of friction is equal to u force normal, and this is going to be 0.4 times 34.9. 0.4 times 34.9 is going to be probably about 8 maybe. Okay, 0.4 times 34.9, 14. Okay, yeah. So we're going to call that 14.0. It's 13.96. All right, so this force is 14. Okay, but that's going to equal to MA. That's going to equal to MA. So unlike before, we're kind of taking each individual component, we're taking it out, and I'm going to show you what it would look like if we put it all together. All right. So we're going to have 14 divided by 4, 14 divided by 4, and so that's going to give us an acceleration of what? 3.67? 3.5? Okay, 3.5, yeah. Okay, so 3.5 meters per second squared. Now, that is down the ramp, okay? We can choose to call that negative, or we can choose to call it positive, and we'll decide later. Okay, now, in the same way, we are now going to talk about our force of gravity in the x, and that's going to equal to ma. So we know that this is going to be mg sine 27 degrees, and that's equal to 4a. So we can dissolve by 4. And notice that this was 4. So those masses are going to cancel out. If you don't cancel out those masses, they're going to cancel out anyway. So it's not a big deal if you don't cancel that out. So now we're going to have 9.8 times the sine of 27, which I think should be about 4.6, 4.7? 4.4. Okay, so our acceleration is equal to 4.4 meters per second squared. Now, that's down the ramp as well. Okay, so we could call that positive or we could call that negative. Okay, all right. So now our overall acceleration is we're going to add this 3.5 and this 4.4, and that's going to give us 7.9. So our acceleration total is going to be our acceleration due to friction plus our acceleration due to gravity. This is going to be 3.5 plus 4.4, which is going to be 7.9 meters per second squared. So that is the overall acceleration down the ramp, how far up the incline is the block going to go? All right, so now we're going to use our kinematic equations. And we know that I'm going to switch over here. We know our initial velocity is 8.5, and we know our final velocity is 0. We know our acceleration is negative 7.9, and we are looking for displacement. So notice here, I called this positive, and I called this negative. I could say that this is negative and this was positive. Okay, so it doesn't really matter. And again, we're going to have a kinematic equation number 4. V final squared is equal to V initial squared plus 2A plus 2AD. Okay, so our final velocity is going to be 0. So now we're going to have negative VI squared, and that's going to be equal to 2AD. And now we're going to divide by 2A, and now we're going to get our displacement. Okay, so 8.5 squared, and then we're going to apply that negative. Okay, and we're going to divide that by 2 times negative 7.9, because that was our overall acceleration. And now these two negatives are going to cancel each other out. All right, so 8.5 squared divided by 2 divided by 7.9 is going to be 4.57. Okay, so our displacement, or our distance up the ramp, is going to be 4.57 we could call that 4.6, and that would be up the ramp. Okay, and so we can see there, if we made this one negative, and then the negative and negative would cancel out, and then this 7.9 would have been positive. Same answer. Okay, so now we are kind of at the end here. Now, once the block reaches the highest point, it will stop. Now calculate the coefficient of static friction. Calculate the coefficient of static friction. All right, I am going to kind of move this over, and we're going to kind of redraw. We're going to redraw the free body diagram. Okay. Now, as the block comes up, right, it's now going to stop. Okay. Now, the gravity, okay, which is what was our gravity? 4.4. So we're going to have 4.4 meters per second squared down the ramp. Okay. And if we multiply that by our mass, 4, this is going to be our force of gravity in the x direction. But this time, this is going to want to come down due to gravity, okay? Which means our friction, our force of friction now, and this is static friction, is going to be going in the opposite direction because it's trying to oppose that motion, okay? So this is going to be mu force normal, okay? So now the sum of the forces in the x direction is equal to 0 because it is stopped, right? And now we can say, again, it doesn't matter which direction we call positive. Okay, let's say down is positive. So we're going to have the force of gravity in the x direction minus the force of static friction is going to equal 0. Therefore, the force of gravity in the x direction is going to be equal to the force of static friction, which is equal to mu force normal. Mu force normal. And we know that this is 4 times 4.4 is going to be 17.6. Okay, so we're going to have 17.6 is equal to our mu. Okay, now our normal force is still going to be, what was that, 25.5? Oh, let's go back and look. Our force, sorry, 34.9, thank you. Oh, I just did it all wrong. Okay, so now we're going to say u times 34.9, and now we can divide both sides by 34.9, and 17.6 divided by 34.9, just a little more than 0.5?
Yeah, it's like 0.5.
0.504. We'll just call it 0.5. Okay, so this mu with an S is static friction, and the mu with a K is going to be kinetic friction. Okay, so all right, I hope that helped, and we will get back to you next time.